Thank you very much to the organisers, to Epifanio. To those of you that have heard parts of this story before, you're allowed to heckle. I'll see you afterwards.
That's gay.
I'm going to, it's not going to be the talk isn't going to be anything like as much theoretical detail as Margarita's talk. It's going to be a little bit of a guide to some of the work that we've been doing and some of the work that we haven't been doing in this area of ferroelectric and ferronematic colloidal liquid crystals. Okay, so my apologies to those of you that know all of these things already, but here's the content of my talk. I'll give you a little description of colloids, and I'll sort of go progressively more complicated before discussing what happens in ferroelectric and ferronematic. I think I may have the wrong order there because I was burning the midnight oil while preparing the talk, and so there may be a mismatch between the beginning and the end, for which I apologize. And there's a wide variety of collaborators on this work from Southampton and from Kiev, and or what is now the generalized Southampton-Kiev axis. Okay, so Oleg is going to give the real story next week, and so let me just give you a little bit about colloids. You've heard me talk a lot about liquid crystal history, so I won't talk about that, but what I will talk about just a little is that in 1861 it was Thomas Graham, a Scotsman who is actually celebrated here in Cambridge, I think, with the Thomas Graham House, who introduced the term colloid, and he compared this to crystalloids, and it's from the ancient Greek term for glue, and colloids in general are droplets of something in something else. And what the something is and what the something else is changes, and there are specific words which chemists know, and probably some of you here who are experimentalists also know. But in particular, the development of colloid science and that of liquid crystal science sort of go hand in hand, and from a philosophical point of view, they are the first exceptions to the sort of ancient Greek classification of solid earth, water, air, solid, liquid, gas. Okay, so here's just a picture. On the right-hand side, there is me with a liquid crystal, and on the left-hand side is a glass of milk. And actually, you see from this picture why it is that, to begin with, at least, people were confusing liquid crystals with colloids because they sort of look similar in a test tube, except that, of course, now probably here is this. Yes, there we are. All right. Of course, we now know that the light scattering, the light scattering that occurs here and in all sorts of other things, white, such as white paint and so on, are because there are, in this case, there are droplets of fat in white paint, and in sunscreen, of course, it's usually droplets of TiO2. And here, on the other hand, we have orientational fluctuations as opposed to density fluctuations that are occurring here. Okay, so as everybody knows, colloidal suspensions are very common, and here in Cambridge they make their business, and of course particularly because of the relationship between colloidal suspensions and food and the way things taste and so on. And there are various words, right, whoops, here we are. Right, so emulsions, liquids in liquids, aerosol, things in gases, right? And in particular, of course, sometimes the particles, they stick together, known as fluctuation, as flocculation, and there are foams, gels, and salts which are related to these things. But the one thing that is in common is the fact that there is strong light scattering. And of course, given the kind of history, theoretical history that I have, I prefer it when they are in thermodynamic equilibrium, but of course, very often they aren't. And as we know, if you prepare, for example, mayonnaise or something like that, and you stir it around, and you put some mustard in there, and the mustard helps the oil and the vinegar stick together, and you leave it around, and you say, yes, it's in thermodynamic equilibrium, and you come back tomorrow, and it wasn't in thermodynamic equilibrium. And depending on who you are, you're either deeply disappointed or you shake it. Okay, so just to give you some idea of sizes, Professor Zanoni is interested in sizes, and so here are the kinds of sizes of the particles that I am interested in, and the particular particles that I am interested in, which will be typical, the ferrofluid particles, and actually what I haven't got here are my ferroelectric particles. My ferroelectric particles in my ferroelectric liquid crystal colloid are typically also of this 10 nanometer kind of size. Okay, so one thing, of course, that we are interested in is what happens to the particles, and of course dense particles as a result of statistical mechanics will sediment, so there are more of them at the bottom than there are at the top as a result simply of a Boltzmann factor. And roughly speaking, if you have relatively small particles, the particles in the air, you wouldn't notice this until you went several hundred meters up. But of course, if it's you or me that are the particles, we notice it rather rapidly, and we notice it rapidly because the typical length scale, and that, I think, is the typical length scale on which the density of particles changes. If the typical length scale on which the density of the particles changes is much smaller than the particle itself, then of course the particle doesn't float around. It just does things according to the usual equations of motion. And in particular, here is the, whoops, shouldn't have that L cubed anymore, should just have G delta rho. But anyway, for a particle with a particular value of delta rho, you know, if I, for example, imagine it of the size of water, typically these are 10 nanometers. So that sort of gives you a, right. Okay. So now let's discuss colloidal liquid crystals. Of course, there's a wide variety of colloidal liquid crystals that one might be thinking about. One might, whoops, there we are. One might be thinking about rod-like colloidal particles in a lyotropic liquid crystal. In a lyotropic liquid crystal, of course, you've always got this water or the solvent background that we try and integrate out of the system, right? But for many purposes, but in fact, these are colloids of some kind. Or they might be suspensions of particles, in which case they could be spheres or rods in a liquid crystalline medium, and that's the kind of thing that I really want to talk about now. But of course, they could also be droplets of a liquid crystalline medium in some kind of mixture of liquid crystal and something else, and typically that was the kind of thing that people looked at in the early days of liquid crystals. And of course, one is interested then in the balance, if you like, between elastic energy and anchoring energy. And so the important things about droplets of liquid crystals is that their shape can be very different from round. And that, of course, was the main thing that puzzled people in the early days of liquid crystals, and people invented all sorts of slightly metaphysical ideas to try and explain why liquid crystal droplets are the shape of liquid crystal droplets. And I think it was Paul van der Schoot, only 10 years or so, less than 10 years ago, who really got his hands on what was going on in this kind of situation. Okay, so colloidal suspensions are usually, it's not always the case, but usually they are less stable in a liquid crystal than the equivalent system is in the isotropic fluid. And roughly speaking, it's because you have to pay a certain amount of energy curvature price, And if you start, the closer you get the particles to each other, the higher the curvature price that you have to pay. And so, it might pay the system not to have to do this and to confine all of the particles rather close together in one corner and to have some kind of phase separation. Right, so roughly speaking, that's a sort of gross overgeneralization, but still, right, that's right. So the colloidal liquid crystal in general will scatter light strongly and it may come out of solution. And of course, in this particular case, I've got homeotropic boundary conditions on the surface, but of course, depending on what the circumstances are, that doesn't have to be the case. Here's a picture, an electron micrograph of some magnetic particles in a liquid crystal that we took in Southampton, just to give you some idea of what these things can look like. They were rods. Okay, here are some pictures taken by Otto Lehmann long ago, which many of you will already have seen, but these are indeed the same droplets that we talked about before, with elaborate director structures that are in the middle. Okay, so here are some length scales that crop up in the problem, and there's a whole variety of length scales. There's the length scale between the particles, there's the size of the particle, there's a typical relay, if you've got an electric field, a typical relaxation length for the system. There's the extrapolation length associated with the anchoring coefficient. And in the cases that I am considering, I'm really going to want the anchoring, the extrapolation length, a term that was borrowed from magnetism, essentially, I think, invented by Michael Fisher at the time that they were looking at the detailed structure of surfaces near the critical point, from which a lot of our liquid crystal work on surfaces was borrowed. But if we have an anchoring, if we have an extrapolation length which is of the order of the size of the system or larger, then we'll probably be able to think of it as more or less a point. Right. Here are some pictures of what happens in rather larger liquid crystal colloidal particles, and you get these elaborate structures about which there was a lot of controversy in the past, right? So here's the Saturn ring, right? It's trying, it's got homeotropic boundary conditions, and you can see that, but there's this electric field that's trying to make the director do something at long distances, and you can kind of see how that there is a problem, but how you resolve the problem, on the other hand, is another question altogether. And right, so here are different ways that people said you could resolve it. Here's the Saturn ring, and here is a sort of a different way of doing it, in which you have an effective defect at that point. And there was at one point a big controversy between the dipole people and the Saturn ring people, and eventually it turned out, of course, that it depended on the parameters, right? So, okay. So just to give so the important point about these things are there are complex structures. They are much larger. The scale of the structures may be larger, considerably larger than the size of the particle. So if I'm looking at this and I've got lots of them, then my optical cross-section, there'll be lots of scattering and stuff like that, and you won't be able to see, really. Of course, you can look at these things explicitly, but if you were looking on much larger length scales, you'd have a strongly scattering medium. And here is, I think, the dipole, a picture of the dipole, and here are some pretty pictures, which I've put there mainly because they're pretty pictures. Oh, okay, all right. And just as a final point here, that actually if you have droplets that are sitting in the isotropic medium, then the kind of wetting phenomena, right, in other words, you'll have a more oriented, the region around one of the particles may be more oriented as a result of these orientational wetting phenomena, and as a result of them being more oriented, the effective interaction between them as a result of just ordinary sort of dispersion van der Waals forces becomes greater, and so they may flocculate, they may stick together, right? And so you can tune the effective potential by changing the temperature very slightly, and these are phenomena that take place very close to critical points, and it turns out that there are a whole set of circumstances under which colloids close to the critical point, colloidal particles close to the critical point of the matrix that is holding them, stick together and give you critical phenomena. So this is not the only circumstance under which it happens. Okay, so let's just try and think a little bit about the thermodynamics of these things, right? In general, that extra energy that you have to pay as a result of the frustration, but right, is going to mean that the pneumatic energy has gone down, has gone up rather, and if the pneumatic energy has gone up, it means that the phase is going to be destabilized. Whoops, sorry. And so the pneumatic phase is destabilized with respect to the isotropic phase, so the phase transition temperature goes down. And in general, there's now going to be a two-phase coexistence. In general, these are straight lines, at least in the region of rather low, of low concentration. And so you can see that there's this region between here and here in which you get phase coexistence, at which you get progressively more and more pneumatic phase before the whole thing resumes. On the other hand, my sort of order of magnitude estimates suggest that if you only had a colloid with, and these colloid volume concentrations can typically be very low, of the order of less than 1%, sometimes of the order of fractions down at 10 to the minus 4, even, then these are relatively narrow, and certainly the normal kind of liquid crystal that you go and buy in a shop, of course, consists of a mixture of a variety of different things. So there's a phase gap at the boundary, and so this isn't going to be comparable to that phase gap. But if you've made a pure system, then this is something that you'll want to look for. Okay, so I've called them dipolar liquid crystal colloids because I want to discuss magnetic particles and ferroelectric particles. And okay, so this story goes back as almost all stories in the liquid crystal profession go back to de Gennes, who suggested that a magnetic colloid in a liquid crystal matrix might couple magnetic and pneumatic effects, and the net effect would be a much larger susceptibility to magnetism, because roughly speaking, you'd have a few particles with a massive couple as a result of that, right? With a massive couple as a result of the magnetic field, and because of the coupling between the orientation of the liquid crystal and the orientation of the magnetic or of the dipolar particle in general, they would drag the liquid crystal particles around. And the idea, at least in technological circles, is that the magnetic threshold, right, the kind of experiments that we do have critical fields of something of the order of 1500 Gauss, and I'll show you some of these things. And the idea is that you might be able to reduce this significantly, and you could switch magnetically rather than due to with electric fields. And my technological colleagues tell me that this is a good thing. Okay, now in practice, we're going to find that the trick seems to work in lyotropics, but not in ordinary thermotropics. Here's a picture of the kind of things that I'm thinking about. So here are my magnetic particles. In this particular case, the magnetic particle, the direction of the magnetic particles is different, is perpendicular to the direction of the pneumatic as a result of the boundary conditions. So these are something to do with the nature of the boundaries of these things, right? It doesn't, the principle doesn't care, of course, whether these are these are perpendicular or in the same direction, because the general idea is simply that you turn these guys around here.
You
Right?
have the two pitches switched, or is it, am I confused? You got a line in field.
Yes.
How about, well, hang on. My magnetic field is up here, right? And my magnetic field is turning these guys around, right? And as it turns around, it's trying to it's also trying to switch the pneumatic, right? So the pneumatic is good.
Then what is orienting the particles up there? They're all with a magnetic moment.
Yeah, oh, I see, yes. They've got a magnetic moment. They've got a magnetic moment because we've cheated. We've cheated by putting a small field on here. Right? We've cheated by putting a small field. I forgot to tell you that
Zero plus.
Yes, I forgot to tell you that we've cheated, and it's called a bias field, and it's a question, right? And all my experimental friends put this bias field in, and there are, I mean, you do get the effect without it, but the maths is certainly easier with the bias field. But yes, absolutely. And I can't quite, I might have a chance to show you some experimental results. I can't quite remember, but the bias field is, I think, was something of the order of 30 Gauss or something like that, and the critical field was something of the order of 1500. Okay. So, yes, the polar particles can be ferroelectric or magnetic, and so the idea is to tune the properties of the liquid crystal for optoelectronic applications. I don't know whether this was what Eugène was thinking of. Probably he just thought it was cute, but the reason that my colleagues are doing it is because they are hoping that they will make some magic piece of apparatus, right? And so the polar particle orientation couples with the liquid crystal order parameter. In these cases, at least in principle, the pneumatic isotropic transition can shift upwards, right? The particles are very small, and because the particles are very small, the idea is they don't stick together, they don't have a massive optical signature. I mean, Martin, I know, does experiments on these things, so he can probably comment afterwards to what extent my idealizations are right. Pardon? Yeah. Yes. Right. And so the idea, at least, is that there will be big increases in pneumatic susceptibility to magnetic electric fields. And the important point is that it would occur at very low volume concentrations. Okay. So let me just talk a little bit about magnetic Right. So ferrofluid, of course, are used in a variety of non-liquid crystal contexts. I think I meant pneumatic ferrofluid, right? They're used in a variety of liquid crystal contexts. The question that Epifanio and Claudio were asking about the local direction, of course, is a sensible one, at least in the context in which we think about it. They don't necessarily have to be ordered. I mean, they will, right? In other words, they probably will pick up some order from the local pneumatic order, but to begin with, at least, they may not necessarily have a magnetic order, and they may have some kind of spontaneous order. So from the point of view of continuum theory, they will, in some sense, be paramagnetic, right? From the point of, if I actually look inside the particles, probably the particles themselves will be ferromagnetic. But on the other hand, if I look at the ensemble of particles that are sitting in my fluid, that's not necessarily, that doesn't necessarily have to be. You're looking very dubious.
Well, no, it's just that the 10 nanometer ferromagnetic particle may be paramagnetic actually on its own, because it's just too small. And you don't have
it is, no, but they can be.
Well, that,
They can be.
yeah, you know, you have a finite size and a specific peak broadness.
Well, let's show you the result. I can show you some experimental results, and of course things are not working the way that we hoped they would work, and it could be that we are making some wrong assumptions, and so let's
So your point is that the ensemble is paramagnetic.
At least that's the way that I look at it, because we have to set. I mean, in the experiments, in the setup that I showed you before, right? We've had to sort of we've had to prepare the system by putting on this field, and if you don't do it, that's called compensated. There's actually words for it in the trade, and you would read a paper in which you'd say that you have either you have compensated dipoles, meaning that they are sort of okay. Right, but nevertheless, the alignment of the free and the magnetic rods is strongly coupled, in the sense that if you have a magnetic order, that will imply some pneumatic order, and the pneumatic order of the rods is coupled with the pneumatic order of the underlying fluid of the liquid crystal. But of course, you could imagine having pneumatic order for the rods, but still not having magnetic order for the rods. Right. In lyotropics, the presence of one has some experimental evidence that this kind of thing actually works. Okay. So here I'm just mentioning these people's work because these people took de Gennes extremely seriously, and it seems to me in some sense too seriously, because he talked about ferromagnetism, and I think what he was more concerned about was trying to switch things. But these people are actually saying that they have seen a proper ferromagnetic fluid. In other words, the system itself is ferromagnetic, thought of, if you like, in terms of individual magnets that are in some sense spontaneously ordering. So I'm not sure. My guess is that such things would have defects in them, and they wouldn't have the kind of properties that we want them to have as a result of the onset of a magnetic field. But nevertheless, I just point these are rather ancient, and as far as I'm aware, between that time and the more recent work, I think very recent work of Martin, these questions haven't been addressed, other than a kind of general belief rather than, I think, a general belief that dipolely ordered fluids was either a difficult, or certainly if you had long-range interactions, was either a difficult or an impossible thing to do. But the general belief, there's a big leap between general belief and actual. Okay, so here, these guys here were actually trying to look for the kind of switching behavior which de Gennes was predicting in 1970. And here are some pictures of the things that they produced. And unfortunately, the pictures are beautiful. And you can see this linear behavior of the, I guess that's the phase difference. So this is some kind of optical phase difference. And I think that they also have this bias field that I was just talking about. And you can see these rather pretty textures. But as far as I'm aware, the work has not been reproduced. And of course, people spend a lot of time trying to get stable suspensions. And it may be that you can't get a stable, that this is the best that you can do, and that this was stable for a day or two, and that if other experimentalists were prepared to have a sample, a colloidal sample that was stable for a day or two, then they might be able to reproduce it. Okay, so now what I'm going to simply do is to think about the Friedrichs transitions, the kind of switching which we are all used to. And our model worries about coupling, and we don't worry about thermodynamics of solutions. And I mentioned that we don't worry about thermodynamics of solutions because actually we have two kinds of order. We have an order that is associated with the colloidal particles, and we have an order that's associated with our underlying pneumatic system, and our theory, in principle, allows that they are both thermodynamic variables in the theory, and in principle our theory allows them to look in different directions, and that might mean energies that are sufficiently large that the particles didn't want to sit in the same part of the sample. So here's my picture of what's going on, and this picture is right. So this picture shows a similar that what you were asking for before. Here are my magnetic particles. Here is my small bias field that we hope has simply aligned the particles in this direction. Right. Here are some angles. Right. So one angle is the amount of is the distortion of the magnetic director. Here's the distortion of the pneumatic director, and so what we want our magnetic field to do, our big magnetic field, this one here, our bulk magnetic field, we want it to change this angle psi, and by changing this angle psi, it moves this angle theta around, and in principle, we want the angle psi to be equal to the angle theta. That's at least our theory will say that the angle psi and the angle theta should be when they're zero, everything is doing well. Okay, so here is the free energy that we used, and the free energy includes, of course, all the curvature terms that we are used to, and there is a natural susceptibility to the magnetic field. There are some terms that say that this F is actually the local colloid volume fraction. And in principle, the local colloid volume fraction doesn't have to be the same. And so it's an entropy term, essentially. And we pay a free energy price if this doesn't remain constant. And here's a term in which which says that the local magnetization wants to point in the direction of the magnetic field. But remember that now I have set the whole thing up at the beginning, so my magnetization is a variable in the problem, whereas if I hadn't done that, I would have to have some terms in there that would allow it to develop, so we have cheated it. And here is a term, an anchoring term. Of course, I haven't integrated in detail over the surface. As far as I'm concerned, it's simply a phenomenological term that says, listen guys, you should be pointing in the same direction. Of course, in the real world, to figure this thing out is rather more complicated. And perhaps I should just emphasize our debt to Professor Reicher, because some of these ideas come originally from him. But this, right, so this thing here, obviously it's partly going to be not the result of a direct interaction, but some kind of relaxation interaction as a result of the, if you like, the total local field that this thing has around it.
And so WP is positive for you.
WP is positive here. Well, I guess in our case, it's negative because I want N and P. Yes, I want N and P to be perpendicular.
Yes, so
yes,
it's positive.
Yeah, right. I want N. Right. Yeah. So, right. So, whoops. Let's come back. Right. Okay. So the idea here, of course, is that, right, this is a linear term. So so the great thing is this is a linear term, and so my linear term is likely to have a bigger couple, right? On the other hand, right, everything is working indirectly through this term, so the hope is that we will have an effective term due to h squared. We're going to ignore this term. I mean, you'll see from our experimental results that this is absolutely not allowed, but I'm going to ignore it in the theory to show you some pretty theoretical pictures. And, right, and right, so what we've actually done, it's called the colloid particles are poled initially by the bias field, and if you work, those that have worked in ferroelectrics, they know that this is something that this is the term that is regularly used in the ferroelectric trade to kind of to eliminate various kinds of domains.
Tim,
Yes.
how could you dot M with HS? I know a bias field set M up, but once you put a proper field on there, it's that which is inducing the magnetism, isn't it? So,
What I'm hoping is that once I've got the whole thing locally directed, it will do as it's told, right? Whereas what you're saying is that, well, maybe it'll relax or something, right?
We've got a very tiny bias field on which sets up the magnetization shows at the beginning. Now you put a much bigger field on. Why should the memory of the bias field be retained?
Well, by that time, it's doing what the big field told it to do.
Yes.
But absolutely, but it's twisted around, and so it's doing what the big field is.
Yeah, but this doesn't imply rotation of the particle. The field, the induced
Right.
moment could rotate inside the particle without the particle
Yes,
rotating.
it could, and then actually there are two different modes here, aren't there? There's which I have now forgotten, but I think we did a calculation that suggested that the particles were rotating. But you are right,
Yeah,
that in
assuming
principle,
that it's rigid in the particles, the magnetization.
yeah.
But then surely the particles should swing around so that the magnetization is simply parallel to the big field.
Eventually, that's what they do.
But
Well,
what you're suggesting now is that magnetization is soft. In that case, you will not actually have.
but the particles do swing round. The
Yeah, but,
particles
I mean, the magnetization is hard, and the particles swing round, so that the gross moment is achieved by turning the hard particles around.
So then the sound this coupling is fine then.
Well,
All right, I think this is a right question, but I don't know the answer to it, right? I mean, from what I understand from reading the literature on similar kinds of things, there are some parameters here, and under some circumstances, the moment swings around within the particle, and under other circumstances, it moves the particle around, right? And there are some parameters, and
This is permanent moment, so I think the
Yeah.
particle would rotate.
yeah.
If you had an induced moment, then you would have an induced moment.
Yes,
there's no
and
bias
poled,
field, and
right,
here you
polling
have
the
a
particles
much,
means physically
higher.
turning them around. It doesn't mean inducing.
No, I was assuming that there's a permanent hard moment there, and you can only redirect it by rotating the
By
particle.
rotation, yeah.
So if you talk about a giant susceptibility at the beginning, surely you apply a field, and then there's a gross magnetization from the bias of the particles, in which case...
Well, if I didn't have a field on, then, right, presumably as many particles would be going. Well, in principle, the particles could go in any direction, and in an isotropic fluid, they probably would. And because I have a boundary condition, because once I have the pneumatic says to the particles, because of this coupling
But
here.
then it would be anti-ferroelectric, because it could be equally, half would be in this direction and the other. So
Yes, and
it would
I
be
mean.
not diamagnetic, but anti-ferro.
Yeah, so I think what people say is that without the bias field, you get as many going in one direction as the other, and then what happens when you have to put the field, at least as I understand it, because people who do. Shall I come on to the experiments in a moment, because I can at least discuss that in the context of the right. Okay, so. All right, so it looks as though, right, the magnet tries to reorient the pneumatic director, right, and so here are just some general comments about what's going on in the theory. What I want to do first of all is just show you some results of the theory, and then come on to some experiments. Okay, so here are the kind of things that we see. Okay, so the kind of things that we see are that there are a number of different regimes, and the number of different I'm afraid these are all in scaled units, and I absolutely, in case translate into real units. I mean, it is possible, and when, if somebody, but But I can't now, and I'll come on later to cases where we have, right? But what we can say in general is that if the coupling is low, then what happens is that we turn the magnet around. The magnet tries to turn the pneumatic around, and then loses contact as we go further. And as it does so, there's number one, which shows what's happening to the angle psi, which is going from 0 to pi by 2. And here's what's happening to the angle theta. It starts trying, and then it gives up. And when it gives up, and so, okay. So this is an ideal case. It's an ideal case where I've poled it, but I've forgotten to put the polling field into the theory. Okay? Right, because, that's it, right? But just to suppose that we have some actual magnetization there, right? So here's this case, and this is kind of interesting, because if you were looking at this, you actually get an inverse Friedrichs transition, right? It's right. You see, this is a linear behavior because there's no threshold to this because of my loss of symmetry at the boundary. This direction is different from that direction, right? Okay, so that's why it comes up from 0, right? But
that angle's in the midplane of the film, right?
Sorry, this is this is an angle in the midplane of it's just to give, it's a kind of figure of merit. It tells, right? So it tells me what's happening. Yeah, right. If it's 0, then nothing is happening at all. Yeah, yeah. I mean, we can also show what the profiles look like, but the profiles are doing sensible kinds of things. Whereas, right, you can sort of guess what the profile is going to be. Whoops, sorry. Okay. So depending on how big the coupling is, and the coupling is roughly related to the amount of the concentration. At least we would think that the coupling was related to the concentration. I mean, of course, right, again, I'm taking once I've got the phenomenological theory, I'm just following through on the consequences of what the phenomenological theory is, right? Of course, if I then said, what is the coupling? The coupling, it's probably something to do with the concentration and various kinds of things like that, and things to do with the actual anchoring and various things. But for the moment, I don't worry about that at all. I just simply say, here is a coupling constant, and I increase the coupling constants, and for low coupling constant, we can disconnect, we can decouple the pneumatic and the magnetic directors. So the magnetic director keeps turning, but the pneumatic director gets fed up and comes back again, and eventually it does what it was doing, right? It was doing before. And as we increase the degree of coupling, right, here we have an inverse Friedrichs transition. Here it decreases as we go towards high fields, and here, right, and only here does it keep increasing as we go to high fields. Okay, right, so actually we didn't solve this by quadrature, we solved it through a set of first integrals, but in a later calculation we did, these are reliable. And we've also done a whole set of asymptotic pieces of analysis, so we know that it really is doing things like these aren't of course I don't know how good the model is, but I know that these are the results of the model as written. Okay. All right, and if you start to take these things a little bit, you then say, okay, well, suppose we do include the field, the transverse field, the polling field, then of course we round, right? Here we have an inverse Friedrichs transition, and here we have something that is slightly rounded, and then you say, well, okay, actually we've got a magnetic field in there, and obviously where what we want to do is to have the concentration such that the coupling between the particles and the director, that piece of the energy is sort of optimized, and what that does is to change the densities slightly, and it means that there will be denser. There's colloidal concentration fluctuations, but the net effect of all of that is that when you do the calculation, you switch this continuous transition into a first order transition. And actually that's how we first spotted it. When my colleagues did this, I should say just blind, without sort of just, turn the handle, what they actually got was things that looked sort of with a van der Waals loop that was somewhere up here, and the question was, where did this van der Waals loop come from? So I think and again, we can, by doing some kind of glorified Landau theory, show that we have a coupling term, which drives a continuous transition first order. Okay, so none of the, yes?
Is F just set to be equal to a constant?
Well, it was in this calculation, but it isn't in this calculation.
So do you have some, is it discontinuous?
Well, what I'm not showing you here are the F profiles, and the F profiles increase in the middle of the system, and they do so differently in this situation than they do in this situation, because in this situation, the magnetic fields, the magnetic particles have been turned around, but the pneumatic particles haven't, and that occurs over almost all of the system, and so it really there isn't much difference in the concentration from one side to the other. But over here, on the other hand, it is, and so you get a jump between one and the other, and you can make a quasi-Landau type of theory where a fourth order term goes negative and the fourth order term goes negative. Tells you that you're jumping from the right. So I don't know whether we can expect anything of this in real life, because we've had to make various kinds of assumptions. If you like, this is a kind of low, a high temperature assumption in a certain sense, that says that we haven't got any change in the density, and then as we reduce the temperature, then the entropic effect of all of these things starts to be okay.
So you don't have gradient terms in F?
We don't, and this is a question you've asked before. We don't have gradient terms in F, and I actually, the way that we should probably do. Let me comment on that afterwards, because
I don't remember asking this question.
Yeah, but I gave the talk. I remember things like this. I wouldn't forget. You always ask the right question.
You went on the receiving end.
Yes. Nothing's ever forgotten.
Yes. No, it's the right question, and let me try and come back to this. What's the time? I'm going to stop in a moment, actually. Okay. So, right. Okay. You can get a higher volume, you can get some magnetic response. Here's a picture somewhere. I have video, but I somehow lost the video somewhere in the computer. But I did have the video last night, but by this morning. But you see, that's what happens when you burn the midnight oil. No, it's somewhere in a different folder, and when you get very tired, you can't search. And so when I rubbed everything out. No, last night. Well, even this morning at 1 o'clock I had anyway, there's a video that shows what right. And we even tried to fit the experiments, but I can't. Right, okay. So here are some sort of questions that one can ask, right? Some are experimental questions, some are theoretical questions. Why is it so difficult to reproduce the experiments of Chen and Lemaire? Is the magnetic director M a real macroscopic variable? You can ask general questions about this kind of continuum theory, which include, whether I want, what's the net effect of grad F squared terms, right? Clearly, in some sense, this coupling doesn't, right? One question that occurs in the literature is that says you must get what they call collective behavior, which is the justification for this magnetic director M to be a proper macroscopic variable in some kind of continuum theory. And I have to say that I'm not I think that this is a question that one wants to ask. The physics that says that the particles are being turned, and as a result of the particles being turned, the magnetic particles being turned, the pneumatic particles will also be turned. I think that doesn't require m being a macroscopic variable or not. Okay, karma, who I notice all of the people that who I had taken care to mention in this talk have, not all, but some have decided not to come and are somewhere else. But,
She's away.
pardon? But yes.
She's in Barcelona.
Really, yes. I spent an exciting day in Akron with Karma discussing the question of making essentially a proper homogenizing this thing properly, right? Okay, and of course there are likely to be interesting dynamical effects. Okay, there is our experiment. Okay, I'm just very briefly going to show you some experiments that we've done in Southampton, and the experiments of course don't involve me touching any piece of apparatus because it will break, but they do involve me going into the lab and people saying, look at that, look through the microscope. Okay, so here is a micrograph, I guess, and of course at least sometimes our ferronematic nanoparticles, they stick together. I mean, I have to say, to begin with, they started to use oleic acid as a surfactant, and I have to say that when we used oleic acid as a surfactant, the particles tended to stick together. They come in this heptane solvent, and then they boil. Eventually, we found a chemist, and the chemist comes from Russia somewhere. He's really Russian, not from Moscow. He's from Abkhazia or somewhere. And he... Sochi, actually, not Abkhazia, but anyway, but the chemist used a different kind of surfactant which worked much better, as probably, I don't know whether the theoreticians know, but oleic acid, of course, is olive oil for all intents and purposes. If.
Really?
No. To me, yeah, now, would I taste the difference? I'm English, you know. Okay. What's interesting, okay, so we did, I mean, what happened when we took our particles, of course, we started with a Friedrichs transition of about 1500 Gauss. And the reason it's not starting suddenly is because my experimentalists, they said, well, you keep talking about the bias field, so we'll put a bias field on. We just put a bias field on anyway. And so by the time the results came to me and I said, have you tried it without the bias field? They said, what? Can you? So, but what's interesting, right, so what you see is that there is, I mean, there's certainly a noticeable effect of putting on these fields. If you look at very low fields indeed, right, the effect is really quite dramatic, right? So in certain sense, it's the low field response rather than the Friedrichs response that is really dramatic, right? So this is a response that you get through optical, simply through looking through it, using, usual kind of optical kind of, cross polarizers and stuff like that. Okay. There's a slight shift to the Friedrichs effect. We can fit to the theory, and when I say the theory is this one, but now, of course, we have a term that looks like that. But it's just this theory, and can we fit our optical transmission experiments to something? We've ignored that term. But otherwise, can we fit our theories to this kind of thing? Of course, I just have a coupling constant here and another coupling constant here. I don't require that they are necessarily proportional to F, although it looks in our experiments as though when you plot them, they are roughly proportional to F. But it seems to me that once I've got the theory, I can at least see it. Of course, the fact that it fits the theory doesn't mean that the theory is necessarily right. Right? I mean, it's certainly possible that people would come up with right. But what we do know is that when we look at, I haven't got any pictures, but we know that when we look at this very carefully, there are no this is the more recent experiments in which we used some fancy surfactant whose name unfortunately I cannot remember, but which was sticking to the particles as part of the process. Okay, I think
I have a
actually,
question.
yeah.
So you show the y-axis as phase retardance.
Yeah.
Does it mean that the experimentalists in your group took account of light scattering and absorption
Well,
and everything,
all
and
right.
extracted just the pure birefringence?
Yes, they plotted what they actually did was to plot. They plotted the intensity that was coming through, and if the intensity fluctuations went through zero, essentially went through zero, we said, okay, we can forget about scattering. And in some of our experiments with higher degrees of nanoparticles, not in this experiment, but in a previous attempt, because this one is, I think, this is proper, this is in the Journal of Colloid and Interface Science, but because soft matter didn't want this one. But soft matter, they said this was just engineering, they said. Me engineering. But in the previous one, indeed, you got oscillations that were that you couldn't fit the oscillations properly because it wasn't going through zero, and this was only happening at higher concentrations. So at higher concentrations, there was some, there were some coagulation effects, and quite. We came back 6 months later and did the measurements again, and the coagulation got slightly higher, but not very much. And when you did that, you could also see some impurities, not the same degree of impurities that Yuri Reznikov. Yuri has a paper in Soft Matter where he said, no, it's nothing like this at all. You can see my particles that have lit up, and there isn't collective behavior, right? But we don't have, we have a little bit of this, right? And you can, and the appearance of the particles in the micrographs corresponds to the oscillations, not right. I don't think anybody looked at side scattering to see what they were, but it's an optics group. I'm hoping they're not making horrible mistakes, but okay. I'm going to stop because I'm out of time, and just simply to say that we also looked at ferroelectrics. They're actually more interesting for various, they're interesting, and the reason that we got here was that we failed with our magnetism. We couldn't do the de Gennes problem, and as a last throw, Yuri Reznikov said, well, maybe ferroelectrics will be better than ferronematics. And in fact, of course, the effect of the ferroelectrics on the phase transition temperature and on various things can be dramatic, although it's important not to make mistakes with impurities in mixed liquid crystals. So let me just say, okay, again, unfortunately, my colleague here, this is a non-standard use of the term Osikov number, but somebody has to become famous, and I just thought that.
I like it.
But anyway, there's a term that is related to the dipolar interaction energy divided by kT, and it turns out that it's important in a variety of different contexts, and it's about 1 in our magnetic systems, which suggests that the magnetic particles should come by themselves, and it's about 10 to the 4 in our electrical systems, and which means that not only should it form chains, but the chains should be so long that they're much longer than the size of the system. And so, I've had discussions with her experiment. Our theories, such as they are, have said, let's pretend that it's not happening, but I think until we know experimentally, I would prefer a cue from it, right? Of course, there are possibilities as to why they might not be forming chains. Here is a term in the free energy that tells you why these systems, the nematic phase, might now be favored, and so the phase transition temperature would go up rather than down. And I'm going to leave all of this other than to show you, oh, here's an experiment, not by me, but by Gary Cook. And you can see that at least in these cases, the oscillations go through zero. So Gary knows what he's doing, at least. And I'm just going to miss all of this out and come to my conclusions and say, okay, so I've talked about the ferronematics, right? Should be very sensitive to magnetic fields. Haven't shown you the results from our Ukrainian colleagues on lyotropics, but things seem to work very much better in lyotropics. Not clear why our effects are smaller than we hoped they would be, but you know, all sorts of possibilities, all sorts of ex post facto excuses we will have when we understand. But unfortunately we don't now. And our experimentalists are saying, well, just give us a bit more time, please give us a bit more money, and we'll put in a new surfactant and it will all work. And certainly some people who wanted either to make bombs or detect them, I can't remember which, showed great interest in our work.
Maybe both.
Like the man in the news, the late lamented News of the World, I made an excuse and left. And ferroelectrics, oh yes, in ferroelectrics, the effect of the important point in ferroelectrics actually was that you will reduce the Frederick's threshold, and your Frederick's threshold wouldn't any longer measure the elastic constant. It would be measuring something else. So don't put some ferroelectrics in there. Say, aha, my phase transition has my Frederick's threshold's gone down. It must be because the elastic constants have gone down. It isn't. It's because there are feedback effects as a result of the susceptibility interaction with the dielectric effects. And here is, I'm trying to make some business for our colleagues here. And right, I think I'm going to stop. And there is no advertisement for a book, but still, if you haven't read my history book, you
Thank you very much, Tim. So I would invite questions now.
yes.
Also, did you do the experiment with a pneumatic with a negative diamagnetic susceptibility,
No.
so that when you switch on the big field, it goes the other direction?
Sorry, what it...
I get.
Oh, you mean with the magnet, the magnetic system? Is
Yeah.
that what you mean? No, I think they have...
Because instead of 5CB, you could use CCH, and in the system where the diamagnetic susceptibility...
So it should have the opposite
so when you
effect.
switch on the big field, it doesn't want to align with this
No,
magnetic
I don't
field.
think they did.
But-
I don't think they did. I mean, I think it was done with E7, right? So that's 5CB, yes. So that sounds like a sensible experiment.
Martin?
I have a sort of a question, general question, which worries me all
Yeah.
the time, is that, I mean, there are some theoretical arguments that when you put a very small particle, like 50 nanometers or
Yeah.
less, into liquid
Yeah.
crystal medium, all these ideas about anchoring
Yeah.
that are orienting the particle are not holding anymore, and so that actually this was the comment that we got from the last referees, that our particles are too small to be
Well, you know, I mean,
considered
if
with
you want
picture.
the problem is if you try and do a back of the envelope thermodynamic argument, you know, to look at these phase boundaries that I did, I can do a back of the envelope argument that says, supposing I have a colloid, and then the colloid is this big, and then there's this amount of distortion, and then there's there's a certain amount of surface free energy associated, and so on and so forth. And then I can do the other limit, which is some kind of Flory-Huggins limit with a sort of adapted Fleury-Huggins with some liquid crystal in it, which is what we did essentially 20 years ago when you were thinking about surfaces. But I can't go from one to the other. Right? What I can say is that my colleagues who were actually looking at the numbers were able to fit our experiments to the theory, right? In other words, we had a set of parameters, and we have lots of results, you know, hundreds and hundreds of points and 2 parameters, and you figure that if you fit hundreds and hundreds of points to 2 parameters, then it doesn't prove, of course. Actually, Banal was in the 1930s when they had these liquid crystal meetings, you know, the big one in London in 1933, and Ornstein was saying, well, I can fit all of the results to my swarm theory. And Banal said, well, of course, it's good, he said, but it's possible that there's another theory that fits it even better. So, you know, I mean, we're not absolutely dead, if you see what I mean. And the physics is obviously, I mean, the physics of turning these things around has to be right. I mean, it's not, you know, whether the numbers are right, but it's inconceivable that you could turn these things around without them having, even if they stuck together, you know, you can ask questions about how much it is and whether they cluster and all sorts of things like that. But they, you know, the idea that the effect wouldn't, that there would be no effect is inconceivable, it seems to me.
It would be nice to distinguish the case of particles that rotate or that just the magnetic moment switches. And you could do that by changing the sign of the magnetic field. Because if it is ferroelectric, the dipole moment wants to go the other way around, and it can do it either leaving the particles still or rotating the particles a full 180.
We have experiments showing.
Oh, you mean what you do? You mean what?
In that case, it is particles rotating.
Yeah,
yeah, which I guessed. Yes.
Right, but certainly we've had a referee that has asked a question about the particles rotating or the moments rotating.
Inside the particle.
Yes, absolutely, and apparently this kind of thing is known in the magnetic, you know, ferrofluid trade, and there are different regimes, and there are criteria for going from one regime to another. But
Ask maybe Martin, you were saying this point of the ferromagnetism at such small sizes, because you have a Curie temperature, and the Curie temperature would go down as you decrease the size of your particles. Conceivably, you can get to the point where the Curie temperature
Yes,
would be as
depends
low
on
as your pneumatic
depends on the
isotropic
material.
transition. Depends on the material.
Yeah,
So-
I think the particles that you were
Well, 10
using
nanometers.
have, I don't know what is the smallest size of this.
10 nanometers, there was
Yeah,
a
yeah, but
right?
then our particles are 5 nanometers thick and
And-
50 nanometers large platelets, and that's clearly, I mean, you can measure it.
So you still have a
Yeah,
peak in
yes.
the diamagneticity.
You can actually measure spontaneous
And
magnetization.
how shifted is the Curie temperature?
That I don't know.
But actually,
Because for any other, I mean, could go down, for a melting transition, would go down 40 degrees, something like that. Water, if you trap it to 5 nanometers, shift the melting point of 50 degrees nearly. And the gas transition in thin films also. So I wonder,
It should depend on the shape of the particle very much as
that
well.
also. But still the size is.
The size and the shape.
And the size and the shape.
in the ferroelectric case, there's been some debate about this in the
Oh, still
literature.
going on.
Right, and I know that one of the groups in Kiev with which I am not coupled, or only very weakly, indirectly coupled, has written a long paper, theoretical paper, about how it could be that the Curie temperature in the small droplet could actually be higher than
That
it
is
was.
because of stress induced.
Yes,
so that
yeah.
is actually a bit different. That's for barium titanate.
Yeah, for
It's the same
barium
thing.
titanate, yes.
And it's changing from the cubic to the tetragonal phase because of the stresses.
Yeah.
But that is slightly different here, that there are not stress.
Stress induced by the manufacturing. Or
The manufacturing, which is done in a mill ball, so these particles actually, if they're bigger, they're not ferroelectric, which is amazing. But if you mill them down,
Then they become-
I mean, not everybody's convinced. People from Bristol are not convinced. HP Labs.
Yeah, but we have experimental evidence from barium titanate.
Yes.
This is this Gary's.
Gary
Yeah.
has shown convincingly that you can
Harvesting
harvest them. That is
methods.
final. That is final. But the origin is not final.
I mean, it is just a monodomain, this is.
That's perhaps not monodomain,
But just a line domain.
Clearly
absolutely
this,
sure, but our magnetic particles,
The
our
magnetic
magnetic
particle is
particles are absolutely not monodomains. Our magnetic particles are very far, because we actually did this calculation, and although I can't remember what the numbers were, you know, we managed to increase the coupling between the pneumatic and the magnetic particles a lot. But when we fitted all of our data, of course, I don't have an independent measurement of what the magnetic moment is, and I asked the chemist whether we could do that, and he couldn't think of a way. But it
GUI
might work.
balance.
Pardon?
A
Anyway.
GUI balance, or
Yeah.
even NMR could be.
Yeah. So, but certainly, if we fitted the effective magnetization of our particles, and we were way off, down by factors of 10 or something from what the maximum value was. And so, it's an obvious question whether you could take the data that we had, do the fitting that we had, and then find some independent method of looking at the particles and seeing whether or not the magnetization of our particles corresponded to the fitting that we did. Because if it didn't, then obviously we would be up.
We did magnetization measurements of both powder and then of our
Yeah.
colloidal suspension, and we get the right
The right order of magnitude. Okay.
very close to what you'd expect.
Oh, okay. All right. So it's but whether you did exactly the same kind of fitting.
No, this is pure measurements. It's just
I see.
concentration.
Yes, but you see, we have what I've
And
done.
you
is
did it with a balance.
is it
Magnetometer, yes.
right? But what I've
GUI
done.
balance type.
Okay.
So may I ask you, if you have a nice experiment would be if you have a material or a powder where the Curie temperature is below the pneumatic isotropic transition, then just by changing the temperature, you could drive the system for having a subsumption of ferromagnetic to non-ferromagnetic and still be inside the pneumatic.
Yes,
Would be
and
cute.
then you would see something.
Okay, but if you go to a chemist and ask him to provide you the material that would have all the properties that you could be sort of covered with a good surfactant that has the right shape and so on, he would probably
Could be
say,
aggressive.
We happened to. One of our people met a chemist at a party. I mean, that's how we got the chemist. He met the chemist at the party. The chemist said, yes, I've got this. There's some method that we're right. So once he got all of this working, that's why he didn't know all of these other methods, because he was good at preparing stuff, but he wouldn't normally have been known what to do with the magnetism. But we might have our samples still, and if we've still got our samples, then it might be that those of you that are more expert in trying to figure out what the magnetization of our particles, because that's a key test as to whether or not we're talking rubbish or not. We could,
It could be easily done for weak ferromagnets. For normal strong ferromagnets, it's almost impossible. Characteristic Curie temperature, it's exchange integral. It's
You had some.
But for weak ferromagnets,
Iron oxide.
No, these particles were produced. The first ones that I showed you were iron oxide particles we bought from Aldrich. But the latest ones were actually probably magnemite, at least the referee. Possibly the referee, was that you? He said it was magnemite. We thought it was magnetite, is it?
How could the referee know?
Oh, because of the colour. The colour. And my experimentalist took some photographs and said, this is is it magnet? Yeah?
Sorry, I missed the word. You say?
Magnetite. Is it magnetite? Fe3O4?
Could be.
Yeah.
Iron oxide.
Yes, well, he took some
Format.
photographs. Well, the thing is that he did some photographs, and he also did, some kind of X-ray characterization? Anyway, under some kinds of characterization, the magnemite and the magnetite look the same. And under some kinds of characterization, and in this particular, the characterization means look at it. If you look at it, they look different. But if you do some other kinds of scattering, then they look right. So referee said, well, this is very interesting, but it's not magnetite.
This poor lady is waiting.
I think we should thank again the team for it.